Assalamualaikum, and my name is Muhammad Anis Mustaqim bin Muhammad Shuaimi, and my metric number is CE210188. Okay, for my part, I will present part A, which is the sampling frequency is equal to 2 FM. So there is two scenarios, which the first scenario is 4 bits and the second scenario is 8 bits. Okay, so the given signal is 5 since 2 pi times 100t, so the frequency is 100. So because fs equal to 2 fm, so 2 times 100 equal to 200 Hz. For the sampling time, ts equal to 1 divided fs, so 1 divided by 200 equals to 0.005 milliseconds. Okay, here are the circuit that I've created in the MATLAB Simulink. Okay, and this is the result of the MATLAB. This is the PCM display result, the digital signal, because it 4 bits, there are 4 signals. Because of that, there is no indistinguishable signal or aliasing happen. This is because fs is equal to 2 fm. Okay, next, here we can see the original signal. Then the bottom here is the quantization process, which is happen in between here. Okay, next, the decoded waveform. Here, this is the decoded signal, which is after the encoded process. Here, after you decoded, you go through here and you got the result. Okay, the Simulink is set for 0.5 seconds. The sampling frequency is 200 Hz with 800 bps. Okay, for the next scenario, which is 8-bit circuit, here is the circuit for the 8 bits. The only difference is here in the PCM display, which is I add 4 more because it is 8-bit. Okay, and this, other than that, there is no changes happen. Okay, this is the result of the digital after encoded process. Yes, 8 because it is 8 bits. Okay, it is the same as before. There is no indistinguishable signal or aliasing happen because it is fs equal to 2 fm. Okay, here is the original signal and the quantization process, and this is the decoded signal. And the simulation is set for 0.5 seconds and the sampling frequency is 300 with 1.6 kilo bps. That's all from me, thank you. Okay, next I will show you how the simulation works. So first thing is I will tell all the blocks that we need to build the circuits. The first block is sampling pulse signal. Then we need a modulation signal, sample and hold 1, we need 2 of them, encoder, integer to bit converter, bit to integer converter, decoder, filter. We also need 2 oscilloscope and 1 display. Okay, then I will run it. So you can see here the PCM display show 4 signals because these 4 bits. Okay, this is the signal. Then we also can see how it's turned into the digital signal. Here are the original signal, and this is the quantization process of the original signal. Then it will flow into the integer to bits converter, and it will become like this. After that, integer to bit, we will go to bit to integer converter, which convert it back to the analog signal. You can see here, this is the quantization process, then back to the analog signal. This is before the going through the filter, and this after going through the filter. Okay, for the 8-bit circuit, there is no difference. Besides, there is small cable going to the display. The process also the same, which is the original signal will go through the quantization process, and then we'll encode it, and then it will convert it into the analog signal again by going to the filter. Okay, so when we run it, you can see okay, so this is the original signal, and this is the quantization process of the signal, which is when the signal is going through here, and then when it going to the encoder, it will become like this, which has a 8 digital signal, because this 8-bit circuit. And then to convert it back to the analog, it will go to bit to integer converter. It will go to the decoder process. You can see here. Okay. This is the signal before going through the filter, analog filter. After going through the analog filter, it will produce a signal like this. And that's it from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zulabi Muhammad Rafian. So I will presenting the part of some of the calculation for part B and part C, and Umi Hamizah will continue for the simulation for this part. Okay, so as what we can see here, we got the sampling frequency Fs. It is larger than 2 FM for the scenario 3, and n bits encoded PCM data is 4, and for the scenario 4 is sampling frequency Fs larger than 2 FM, and the n bit encoded PCM data is 8. So based on the question given on the sampling, so t is equal to 5 sine 2 pi 100t is more than according to Nyquist. So we define the according values to the table above, provided the encoded for bits encoded PCM in the table and scope diagram with the respective quantization interval. So increase criterion, which is what we can see here, is Fm is equal to Fm is equal to 100 Hz. So as what we can see from the table above, the sampling frequency Fs is more than 2 FM. So 2 FM times 4, we get 8 FM, and the sampling frequency Fs, it is equal to 8 times 100, so we got 800 Hz, and then the period we got 0.000125 seconds. So this is the graph that we gathered from the 4-bit encoded PCM data. Okay, and this is the oscilloscope diagram, and this is the quantized signal. Okay, for 8-bit encoded data with the PCM data, so this is the digital form of the 8-bit encoded PCM data. So we got time for each amplitude, and then whereas the time is in milliseconds. So as what we can see here, for the 8-bit encoded PCM data, the amplitudes of the quantized signals is quite differ to the 4-bit. Okay, and then this is the oscilloscope for the 8-bit. So figure above show the modulation signal after have been encoded and decoded by using 8-bit encoded PCM data. Okay, so for part C, the Nyquist criterion 100 radian per second, and then we got 15.9155 Hz, and the sampling frequency we got the Fs is equal to 2 FM. So 2 times 15.9155, we got 31.0 31 Hz. So we put 20 Hz for sampling frequency, which is less than 2 FM. So for the 4-bit encoded PCM data, we got is what I can show here. And then this is the quantized signal and the scope diagram. And the figure above show the modulation signal after it's been encoded and decoded by using 4 bits encoded data. So for further explanation upon the structure of the graph will be explained in the simulation. So that's all from me, Muhammad Zarif, and I will continue to Umi Hamizah. Thank you. Assalamualaikum.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Umi Hamizah binti Said. So in this video, I will present to you the simulation for part B and part C lah. Okay, so as you can see here, this is the table 2 and table 3 that provided in the PDF file in the lab sheet lah. Okay, so based on this table, I have do my simulation in the MATLAB Simulink. Okay, so this is our circuit lah, which is the circuit I follow with from here, which is PCM encoding and decoding in MATLAB Simulink. Okay, so I will run the simulation right now. But before that, so this is our period value, which is 0.00125, and pulse width is 0.125. The calculation just as showed by previous group member lah. So this is the how I get the period value. Okay, so press OK and then I will run lah. Okay, as you can see here, this is the result. And okay, for the quantizer, I got this, and for the oscilloscope I got this. Okay, so basically we have 3 types of graph lah. Okay, so this is for 4-bit for the part B. Okay, so next I will simulate for the part B for 8-bit encoded PCM display lah. Okay, so for the period I use 0.00125 same, and the pulse rate is 0.125. Okay, and the frequency 100, and then this is 8-bit lah, 8-bit encoded PCM display. So I will run. Okay, so this is our result lah for the 8-bit. And then for the quantizer, we got this, and for the oscilloscope we got this form. So there are 3 and this. Okay, as you can see here lah. Okay, so we proceed with the simulation for part C, which is part C also 4 bits lah. And then for the period, as you can see here, I have set it to 0.05 and pulse width equal to 5 lah, according to the word file that I have that we have calculated, which is we put 20 Hz lah for the sampling frequency, which is less than 2 FM. So from that we put it 0.05 because 1/20 is equal to 0.05. Okay, so I will run. Okay, so this is the waveform lah for the 4-bit encoded PCM display. Okay, and then for the quantizer, okay, so this is for the this is the diagram for the quantizer and the waveform. And then oscilloscope. This is our oscilloscope, from our oscilloscope lah. Okay.
And Assalamualaikum. My name is Bev30103 Bbl2 G1 and my metric number is AE190076. So now I will discuss about part D of PBL2. So what happened to the resultant recovery modulating signal if the amplitude changed to 15 volt and 0.5 volt. So this is the waveform of sampling pulse signals of 4-bit encode PCM data of 15 volt, and then this is the waveform of the resultant recover modulating signal before the process of filtering, and then this is the waveform of resultant recovered modulating signal of 4-bit. We can see the amplitude clearly, which is this is not very smooth. And then this is for 8-bit of 15 volt, and then this is the waveform of sampling pulse signals. Okay, and then this is the waveform of resultant modulating signal of 8-bit, and then this is the 0.5 volt of 4-bit PCM data. We can see the waveform of sampling pulse signals. And then this is the waveform of resultant recovered modulating signal of 4-bit 0.5 volt. You can see clearly it was very smooth of the amplitude. And then this is the 8-bit encode PCM data of 8-bit. Okay, this is the waveform. We can see it very smooth compared to 15 volt. The amplitude was very smooth compared to 15 volt. So the signal of 0.5 volt amplitude is smoother than the 15 volt amplitude when the waveform of the resultant recovered modulating signal from the 4-bit and 8-bit encode is azimuth, and then the step size and quantum size error have decreased since Vm equal to 0.5 volt, and as a result the signal form becomes smoother and more precise. Okay, and then next, this is the method used for improving the resultant recovered modulating signal. Okay, based on component D, we employ the same amplitude, which is 0.5 volt, and then other block value as before. Okay, to improve the waveform of the resultant recovered modulating signal, which can be compared to the modulating signal we gain from the previous figure. Okay, this is the waveform of modulating signal, and then this is the waveform of the resultant recovered modulating signal. Okay, the waveform of the modulating signal and the resultant recovered modulating signal are comparable in the figure above. As a result, our approach is increased gain has been demonstrated to make the recovered signal which is similar to the modulating signal. Thank you.